We're in section 8.7 where we are going to discuss indeterminate forms and L'Hopital's rule. Recall that forms of 0 over 0 or infinity over infinity are called indeterminate because they do not guarantee that a limit exists, nor do they indicate what the limit is if one exists. So let's just do a little review of what we would do to evaluate limits when we come up with 0 over 0 or possibly infinity over infinity. So here's one example. We're looking at the limit as x approaches 3 of the square root of x plus 1 minus 2 all over x minus 3. And we end up with, if we plug in 3, we get 3 plus 1 is 4, so the square root of 4 is 2 minus 2, so there's 0 up top. And if we plug in 3 here, we get 0 in our denominator. But what we learned in Calc 1 about evaluating this type of limit is that we could rationalize. And in this case, we're going to rationalize our numerator since that's where the radical is. So I'm going to multiply top and bottom by the square root of x plus 1 plus 2, the conjugate. We're going to multiply top and bottom by the conjugate. Okay, when I do that, we get the limit as x approaches 3 of x plus 1 minus 4 over x minus 3 times the square root of x plus 1 plus 2. Okay. Of course, if we simplify our numerator, we see that that simplifies as x minus 3. And on the bottom, we still have an x minus 3, so those are going to cancel. And we're left with the square root of x plus 1 plus 2. And of course, up top, we have a 1 here to hold the place. So now I can plug in 3 to evaluate the limit. When I do, we get 1 over the square root of 3 plus 1 plus 2. And that comes out to be 1/4. All right, so that's one technique when we had an indeterminate form. All right, let's take a look at another example. Okay, here we have the limit as x approaches, and I think there should be a 5 here, of 5 minus x over x squared minus 25. All right, so when we take a look at this, plugging in 5, I get a 0 up top. And in the denominator, if I plug in 5, we would get 0. So again, we have the indeterminate form of 0 over 0. We don't know how to take the limit of that. 0 over 0 doesn't mean anything to us. So we need to do some type of algebraic manipulation to help us evaluate this limit. And for this one, I believe we can just factor. So we're going to look at the limit as x approaches 5, and this is, I'm going to factor out a negative to turn this around. So we got negative x minus 5 over x minus 5 times x plus 5. Okay, of course, the x minus 5s cancel out. And so now we're looking at the limit as x approaches 5 of negative 1 over x plus 5. Okay, and of course, we can plug in 5 now, and we end up with negative 1 over 5 plus 5, or 10. Okay, so we were able to evaluate that limit. All right, hopefully this is bringing back some memories from Calculus 1 for you. In this next example, we have a polynomial. Okay, and we're looking at the limit as x approaches infinity. So if we evaluate in each of these pieces, of course, as x gets larger and larger and larger for 5x cubed, that thing is going to continue to get larger. So we get something that's getting larger plus 1. The whole numerator is going towards infinity. All right, and same thing's happening in our denominator. We got 10x cubed minus 3x squared plus 7. As x gets larger, this thing is going to continue to get larger. So we end up with infinity over infinity. So what we would do in this example is actually look at the highest power of all of the powers in the expression, and we're going to divide top and bottom, numerator and denominator, by that power. So in this case, the highest power is 3. So I'm going to look at the limit as x approaches infinity of 5x cubed plus 1 over x cubed over 10x cubed minus 3x squared plus 7 over x cubed. And of course, that's going to simplify as the limit as x approaches infinity. Okay, if I distribute the x cubed, we get 5 plus 1 over x cubed. And in the bottom, we get 10 minus 3 over x plus 7 over x cubed. Okay, well, in Cal 1, we're right at the point where I can't recall the exact theorem number. It may be 3.10, but it talks about the limit as x approaches infinity when we have c over x to the n, where n has to be a positive number. It has to be greater than 0. And it tells us that this limit is 0. Okay, if we got a constant over some power of x, positive power of x, as x gets larger and larger and larger, this entire expression goes to 0. So I can continue to evaluate the limit here by looking at the limit of each term. I need to look at the limit of 5, of course, which is just going to be 5. The limit of 1 over x cubed is going to be 0 according to this theorem. Okay, so we got 5 plus 0 in my denominator. We get 10. All right, same thing here. We got a constant over x to a positive power, so that's going to be minus 0. Same thing here, plus 0. So we end up with 5 over 10, or 1/2. Okay. Yes, and I'll try to provide a link to that video that talks about some of these more basic methods for evaluating our limits. All right, here's another example of an indeterminate form. We've got the limit as x approaches 0 of sine of 6x over 4x. Okay, well, we can evaluate this using this special trig limit. It's worth remembering these special trig limits because they pop up all the time, it seems. But it says the limit as x approaches 0 of sine x over x is equal to 1. Okay, but the thing is that these have to be the same in order for this to work. So when I look at this limit, I can rewrite this as 1/4. I'm just going to factor out the 4 from my denominator. Okay, and I'm going to write this as the limit as x approaches 0. Well, we've got sine 6x up top, and in order for this to work, we need 6x in the bottom. Well, I already have the x, but what I didn't have was the 6. So to compensate, we're going to multiply by 6 on the outside. So those would cancel each other out. Okay, so what we get is 6/4 or 3/2 times the limit of 6x over 6x. Well, according to the special trig limit that we have here, that's just 1. And so our final answer is 3/2. Okay, so we have been able to evaluate some limits when we got indeterminate forms using algebraic manipulation, but that's not always possible. So how else can we do that? We're going to take a look at L'Hopital's rule. Okay, it applies when we have an indeterminate form. Okay, it says let f and g be functions that are differentiable on an open interval a, b, containing c except possibly at c itself. Assume that g prime of x does not equal 0 for all x in a, b, except possibly at c itself. If the limit of f of x over g of x as x approaches c produces the indeterminate form 0 over 0, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. Okay, so basically, in order to evaluate the limit, we can take the derivative of the numerator, take the derivative of the denominator. It should give us the same limit as the original expression if the limit of the original expression was the indeterminate form 0 over 0, or any of these other indeterminate forms, such as infinity over infinity, negative infinity over positive infinity, and all the different permutations listed there. Okay, so this is good. This is going to be a good way for us to evaluate limits as long as we recognize that we have one of these indeterminate forms that is listed. All right, it says another form of L'Hopital's rule states if the limit of f of x over g of x as x approaches infinity or minus infinity produces the indeterminate form 0 over 0 or infinity over infinity, then the limit as x approaches infinity of f of x over g of x equals the limit as x approaches infinity of f prime of x over g prime of x, provided the limit on the right exists. Okay, so we may use this form a little bit later when we look at some of our examples. Okay, but let's just revisit the previous example that we did. We actually used algebraic manipulation to evaluate the limit as x approaches 0 of sine of 6x over 4x. Okay, but we can evaluate this limit using L'Hopital's rule, because we saw that if we plug in to evaluate this, we get sine of 0, which is 0, and then of course 4 times 0 is 0. So since we get the indeterminate form 0 over 0, then we can use L'Hopital's rule. So L'Hopital's rule says, okay, well, I'm still going to take the limit as x approaches 0, but now it's going to, the limit of the original expression is going to be the same as the limit of the derivative of the numerator over the derivative of the denominator. We're not using the quotient rule. We're actually taking the derivative of the numerator and denominator separately. So the derivative of sine of 6x is cosine 6x times 6. And then the derivative of 4x is just 4, okay? Which makes everything better because now my denominator cannot be 0. I have a constant there, okay? And so now if I try plugging in, we get 6 cosine of 0, because 6 times 0 is 0, over 4. Okay, and of course cosine of 0 is 1. So we find that the limit is 6/4 or 3/2, which is what we found it to be before. Okay, so we could have done this using algebraic manipulation or using L'Hopital's rule. But we can only use L'Hopital's rule if we have one of these determinate or indeterminate forms. All right, so let's take a look at some other applications or places where we might use L'Hopital's rule. Okay, we've got the limit as x approaches 0 of the square root of 25 minus x squared minus 5 over x. Okay, and if we try to just plug in 0 to evaluate this thing, you should see that we get 0 over 0 because our numerator would be the square root of 25, which is 5, minus 5, so that's 0, and then in our denominator we'd have 0. So because we have an indeterminate form, we can use L'Hopital's rule. All right, and when I do, we're still looking at the limit as x approaches 0. Okay, of course, this is 25 minus x squared to the 1/2 power. So when I take the derivative, it's 1/2 times 25 minus x squared to the negative 1/2 times negative 2x. Okay, of course, the 2's cancel. All right, and then, of course, we would evaluate the derivative of our denominator, and it just turns out to be 1, okay, which is great, right? So that simplifies everything. So I can find the limit if I can evaluate the limit of, looks like we have negative x from over here over the square root of 25 minus x squared. Okay, and that looks great because I can plug in 0, we get negative 0 over 25 minus 0, or the square root of 25 minus 0. 0 over a non-zero number is 0, so we were able to find the limit. All right, what about C? All right, if we tried to evaluate the limit as x approaches infinity, does this give us an indeterminate form? And the answer is yes. Okay, in this case, x is getting larger, and as x continues to get larger, so does natural log of x cubed. It just keeps going, growing and growing. So we get infinity up top, and then on the bottom, as x gets larger, so does x squared minus 1. It continues to grow. All right, so we get the indeterminate form of infinity over infinity, which is one of the valid forms that allows us to use L'Hopital's rule. So since we got this indeterminate form, we're going to take the derivative of our numerator. All right, so the derivative of natural log of u is 1 over u du. So we get 1 over x cubed times 3x squared. Okay, that's our derivative in our numerator. And in our denominator, we get 2x. All right, so the x squared cancels, okay, with all but one x in our denominator. So we've got the limit of 3 over x over 2x. Okay, so do we still have an indeterminate form? Well, here we have 3 over x. Well, if we plug in, well, what happens when we get this thing larger and larger and larger? This actually goes, the whole thing goes towards 0, right? As x gets larger here, all of this is going to go towards 0. Here in the bottom, as x gets larger, it's still going to go towards infinity. But I think what I want to try is a little algebraic manipulation here. Okay, we've got 3 over x, and that's the same thing as multiplying. Since it's divided by 2x, we can multiply by 1 over 2x. Okay, And so that gives us 3 over 2x squared. All right, we're still taking the limit. We haven't evaluated the limit yet, so let me put my limit notation back in here. Of 3 over 2x squared. Okay, well that takes us back to the theorem that I introduced from chapter 3 a few pages back, because we can write this as 1/2 times the limit as x approaches infinity of 3 over x squared. Okay, and what we saw was when we have a constant over x to some power. Okay, let's go back and look at that. It was kind of informal, but we had that in chapter 3. Went too far. Okay, when we have the limit as x approaches infinity of a constant over x to some positive power, that limit is equal to 0. All right, so that's what we have here. Okay, so we've got 1/2. We got a constant over x to some positive power, so that's 0. Our limit is equal to 0. All right, we have D here, and this is the limit as x approaches infinity of x cubed over e to the x squared. All right, so if we first kind of think about what happens as x gets bigger and bigger and bigger for our numerator. Well, since this is x cubed, the larger x gets, this thing continues to get large, right? So right now, we can say that the numerator is going to go towards infinity. And then we know what e raised to some positive power looks like. The exponential function grows like this, right? So not only is it just e to the x, but it's e to the x squared. X squared is also increasing. So we got lots of increasing things, but this gives us the indeterminate form of infinity over infinity. All right, so we can apply L'Hopital's rule and say we're looking at the limit as x approaches infinity of 3x squared. Okay, that's the derivative of the numerator, and the derivative of the denominator is e to the x squared times 2x. Okay, so we'll try to evaluate the limit now. Of course, this x can cancel with 1 in our numerator. We've got the limit as x approaches infinity of 3x over 2 e to the x squared. Okay, well, if x is approaching infinity, then both our numerator and denominator, they're still both going towards infinity. 3x is going to continue to get larger, and 2 times e to the x squared, it continues to get larger. So guess what? I'm going to apply L'Hopital's rule again, because we got infinity over infinity again. So we get limit as x approaches infinity of 3 over 2e to the x squared times 2x. Okay, or the limit as x approaches infinity of 3 over 4 e, well, I'm going to say 4x e to the x squared. All right, so notice here what we have is a constant, right? This thing is not changing. So we can probably figure out what the limit of the entire expression is if we know the behavior of our denominator. And so we've got 4 times x, which is getting larger, it's going towards infinity, times e to the x squared. It's getting larger, right? So the entire denominator is blowing up. And the larger our denominator is, then the closer this entire thing is going to go to 0. Right? If we have a constant, as the denominator gets larger and larger and larger and larger and larger, then we can say that it goes towards 0. So the limit as x approaches infinity of x cubed over e to the x squared would be equal to 0.